But I usually covered it in the software. So we're talking about, my ideas. I'll show you. She goes no, I'll be very much.
Hey, Prince. Say hi. Yeah, right there.
Good one. How are you doing?
He can't hear us. I mean, we can't hear him.
Let me continue on this class notes and try to finish the rest without going into too much detail. This is the last slide of section 2.3. Last step here. But for the last 3 years ready for learning, and basically these are the 3 possible screening criteria, either by screening until all the nodes are pure. That results in too much screening actually. So no cases all belong to one class, right? So the pure for all nodes, for all the terminal nodes. Or contains cases having identical feature vectors. If you have all the feature vectors are identical, there's no way you can further split, right? Okay. That's another criteria. And actually the RPART package use adopted number 3 until the conditions that the number of cases in this node, which is something set minimum size. So I'll talk more about that. We have this RPART. Okay. So basically, the package RPART adopt the third criteria. For in the trees and then for printing the tree. Actually, printing a tree, just a print, this kind of branches mean that from a particular node, we cut all the descendants from that. It's only that node to remain. That's also cutting separation. So that's the idea of that. And the print subtree is the one that is obtained by successively printing of branches, but depend on certain criteria, of course. Too much of this technical details. Okay. The problem is that there are too many ways of, say, obtaining subtree. So need some kind of goodness criteria for obtaining a subtree. So one of the solutions using so-called minimum cost complexity printing. So basically, the implementation of RPART is based on that. There's a complexity parameters to be set. Let me just for once explain that. Just use the final result. The last, on this slide, this is slide number 3, so section 2.4. Okay? Complexity of a tree space is the number of terminal nodes. That's called complexity. Okay? So, complexity node means that how many terminal nodes you have in the tree. Okay? And so-called cross complexity measure of the tree is that here this is some kind of probability of misclassifications in all the terminal nodes combined. Okay. Of course, here we are able to figure out Well, basically, this is the error rate in the classified result. Okay? So from all the terminal nodes, what is the probability of misclassified observations in the tree? Some value, some complexity parameter. This is the CP we're going to talk about later in alpha control parameters. Okay? So it's called complexity parameter. Alpha times complexity of T. So basically, the idea is that, of course, you can consider if alpha is 0. That means if alpha 0 means that we are not considering the complexity of T. So you can keep going your trees and the tree become too complicated. Way too many nodes. Okay? And then with some value, some positive value alpha multiplied by the complexity node means that we penalize for a tree model which is too complicated, right? Of course, you can go trees indefinitely until all the nodes are pure, so then here the misclassified probability will be 0. But then, before we reach that, the tree become more complicated. The goodness of the model and the model complexity. Okay? Too many nodes, then we penalize with certain positive alpha here. Make sense? Okay. So you could have like 2 trees under comparison. Say, of course, if you have 2 trees with the same complexity, same number of terminal nodes, and one tree that attain a smaller misclassified probability, that means that tree is better. But what about between 2 trees? One is more complicated model with a small misclassified result. One is with a slightly less number of terminal nodes, but with slightly larger misclassified result. So you try to balance between these two. Okay? So here this is misclassified rates, and then here this is penalizing the model complexity. Okay? Actually, that's idea so-called cost complexity measure. And the idea is obtain the minimum cost complexity pruning trees and then whatever that is. And of course, we already said that. I already said that if you set alpha equals 0, basically small subtree with smallest misclassification cost. But the one with all nodes that have been pure, of course, that would be the one that you have the minimum result. But then in that case, the tree is just way too complicated. You have too many nodes in there. And then if you penalize too much about model complexity, then basically you end up with only just a root node itself. Right? So actually we try to balance between a good model and complex model, right? Complexity. Okay. So here usually the idea is that finding a good model is that the model has a good prediction power, but at the same time also ideally also it's a simple model. Easy to interpret. Okay. A lot of this model, the goodness criteria is actually based on this idea. Okay. You try to balance between the good prediction power and then the model complexity. Okay. The idea is that if possible, try to find simple model that has a good interpretation power, good prediction power. I think we can forget about this algorithm and it's set to okay. Of course, we try to find what is the optimal tree to come by. Okay. The question is which subtree has a better generalization performance. When we talk about generalization performance means that with your tree model or whatever other model you have, you apply this to the test data set. Okay. So less test error will be the one we look for, right? So how should we choose alpha? What value alpha to choose? Okay. One solution is that do the V4 cross validation, and by default, alpha set this V equal 10, so it's 10-fold cross validation. Right? In our class note, our next class note, I will elaborate more on this choice of this cross validation. Okay, so use a V4 cross validation. And there's one thing that is adopted also in this pruning the tree is so-called, or to come up with the optimal tree is so-called using the one standard error rule. which is sort of close related to Bernoulli model. Right? Okay. Or whatever type of testing error you're looking for, okay. The test error for a tree on sample L2 with N2 cases basis is the average. This is average misclassified, well, or the classified rate, right? Misclassified rate, isn't it? Okay. Meaning that for that knows that supposed to be in class JN, but it's not. Okay, so that's misclassified rate. So you take in the error rate. Okay. So proportion of misclassification base is the one that we're testing, and the standard error of that base is a hit or miss, right? It's a success or failure. So it's actually the standard error for that is here by this, isn't it? Right? So this is like we have. This is the proportion, the standard error for proportion of success, just given by that. So binomial error counter distribution, we have this result. Okay. And usually it's adopts so-called one standard error rule. Is that one standard error rule chooses trees that so that it's full right below this one standard error for that. And then usually in our part, when you try to plot this complexity measure, they would plot this one standard error as well, and usually it's dash line to see. We're going to see example later. Try to run through that. Okay. So one standard error rule will apply to that. Chooses the simplest tree. The accuracy is comparable to whatever the case that we come back to this. Okay. So we have an example of it. And actually, part of this we already talked about handling missing value. Okay. There are two circumstances about missing value. Missing value could occur in learning sample and could occur in testing sample. And there are three ways to handle the missing value problem. Discarding that probably our first way, but usually it's not this is probably not the way to go. Okay. Just discard any cases with missing values. Okay. This may lead to serious depletions of learning sample. Meaning that if this is probably the case, right? If discard too many observations with only just a very smaller number of observations available in trend sample. Okay. So probably not the way to go. The second way is for continuous attribute, you can impute missing value with average, with averages. Under unstructured missing value situation. Missing by random. Okay. If you have missing by random, you can do that. Usually it's hardly the case, right? You still have to look at how missing value occur. And categorical attribute simply just treat missing value as a new category. So that's a way to do it. Okay. And the third answer is to use a surrogate split, and this is what is adopted by our part. I mentioned this already, right? And node rank the optimal splits on each attribute, okay, for that node. Okay. Now, if the value of the attribute used by the best split is missing, then use the second best split. If not, if second split also missing, use the third split. Until that all missing. What happens if all missing? Okay. They basically assign that observation to the so-called maximum direction, meaning between the left split and right split, which one contains more observations. Just assign that to that. Okay. So something is strange about this. And usually, of course, in our part calculation, if you specify too many of these surrogate split, and that's where you can specify number of surrogate splits you want to retain it in the model. Okay. More surrogate splits means that more computation time. About half of computation time will be devoted to this. So it's computing, retaining, and computing this surrogate split. There are some other issues that could arise in the tree model. Is that the variable selection is biased to variables having more distinct values. Okay. So actually, this would be the case. Okay? If you have more distinct values, like one variable is having, let's say for the time being, look at the continuous variable. Okay, and this one variable has like say 50 distinct values. The other variables has having like how many, maybe say 100 distinct variables. Usually the split is favored on the variable with a less number, with a more number of distinct variables, with the one with hundreds. Okay. And if you have a nominal variable having a large number of labels, usually that is also the one that will be favored by this tree model. What is that? Remember we talked about that. Number of possible splits for nominal variable. Okay. Suppose you, so if say you have a nominal variable with L levels, right? Okay. Okay. You have this many levels, and the number of possible split for that is 2 to the L minus 1 minus 1. Right? We talked about that already, right? Okay. Now think about that. For a large number, or for a nominal variable having a large number of labels, what happens to this? Assuming say L is 16, how about that? Okay. L is 16 to the power 15 minus 1, this is close to 32,000 something. Okay. Anyone who took my last course, you should remember that number. Right? 2 to the power 15 was what was that? 32,676 or something like that. We talk about that number, but anyway, we can calculate, right? It's okay. But think about that. So you have this many possible splits. Okay, if you have more options. Usually, your split, the tree model will be tend to favor that variable to split on that variable first. Okay? So that creates some kind of bias, right? So there are some. So here, this could be issues on that. So variable selections bias toward variables having more distinct values. Okay. End cut is that you have a very unbalanced result. One channel has only few observations, the other channel has a huge number of observations. Okay, that's called end cut. So end cuts are favored over middle cut, right? Okay, and the tree method is only one step optimum. Okay, doesn't look at overall optimum. So to R-plot, there's an alternate package called Party, okay, P-A-R-T-Y, and there's some associated for some other package built on that Partykit. Okay. They do a different ways of like tree model. It's a nice package, right? Okay. Nice name. Okay. And Partykit is built on top of Party. So in there, they instead of this, they use a conditional inference about the splitting the trees. Okay, and they offer some kind of statistical method of validating which split is better. So actually, this is an entire set of different tree models. So there they consider sort of overall optimum in that case, okay? Not just a one step optimum. And it's quite unstable. Okay? Instability is one shortcut of this tree model. If you try to jitter the data values a little bit, means change. So you just impute certain small amounts of variation in the data set that would completely vary your tree model. Too sensitive. And lack of smoothness in the prediction surface, probably not for classification. Okay. Remember, tree model can also be used to case other than our classification task. Here, we only talk about classification task where response is categorical. If you have like a continuous response, including survival data, it's different. Surface will be very rough. Okay? So lack of smoothness in that type of model. So that's a drawback about this tree model. Okay, should I close the door? Close the door. I'll go to part of this and then we pick up our node 10.r and continue on that. And actually at the time, for the time being, I also put the node 14 for now, okay? Because that is related to variable importance. I think a lot of you have confusion, and I think the example I gave you is not exactly correct. The one I say model 3 is not exactly model 3. Okay? There's another command called filter variable importance that actually can model 3 variable importance. So I'm going to pick up on that. Okay? Model selections and assessment, I will go through this quickly, and just a lot of this we just pick up on the ideas, why consider. Of course, I guess you have learned this from linear model, right? Some of this model goodness criteria. Okay. So I guess some of these I'll consider as just a review. Okay. The basic idea is really simple. Okay. For training, validation, and test error, they have two basic objectives: model selection. You want to choose the best model based on performance measures, and performance measures is conducted based on the test sample. Okay. The model assessment estimates generalization error. So that's the test error of the final model. Model selection and model evaluation or assessment. Okay. See which one is better. Okay. And error types basically there are three types of error that one could occur on training error, fitting model. Okay. Basically, this is on the fitting model, and validation error, selecting model. This is prediction error. And test error, generalization error. Hopefully, we can find one model that actually reduce training error and reduce prediction error at the same time with a good generalization error. Hopefully, okay. So that's a target. Okay? So we have these three error types. And the method is like, well, of course, here they are just use some model criteria measurements. Okay? Like Merrill CPs, these are high key information criteria, basic information criteria. And actually, in the tree model, the one we have seen there, that's a sort of one type of criteria, very similar to any of this. Okay. Actually, they try to balance between model simplicity and the prediction part, right? Or reducing the error. Okay? Try to balance between these two. Okay? And second method is totally out of this. General method is like using resampling. Okay? You can do cross validation. You can do bootstrap. Okay, on the result. Okay? I just try to cover this quickly. Okay? The general approach to model selection assessment is that when you have a large data set of variable, ideally you would split the data into three sets. I actually mentioned this already. Okay? So let me formally introduce this part. Okay? Split the data into train set for model fitting. So basically, this is a part for what is that? Let's say what was the first one? Okay. Fitting model, right? Training error. We try to fit a good model, and of course, at the same time, evaluate this training error. And validation set, we see the prediction error. Okay. For estimation of prediction error for model selection. Okay. And test error, basically, this is the part where you want a good result also, right? That is for assessment of generalization error or test error for the final model. And the Hesse et al. Suggests this kind of split. Okay. But actually, this is the book I gave a link to, right? Isn't it? Okay. That big what is that? ES. What was the name? What was the name of the book? Like ESL? Right here. The first one, okay? Oh, it's ESL, that's right. The Elements of Statistical Learning, okay? That book, okay? One of the authors has it. Okay? And it was suggested by them. Actually, not only in the book, they have some earlier papers about that. Okay? They suggest this kind of splits for train, validation, test set if you have large data set. Okay? If not, you have a moderate data set, then you divide the data only into trend set and test set, okay? Only two parts. Okay, and use a trend set for two purposes. Okay, model building and validation. Okay? And test set is only used to verify the generalization error. Okay. And for validation purpose, in model selection, use a 5-fold or 10-fold validation. So for this, we take this opportunity to talk about validation. Okay. Later, yeah. Didn't open as this. I'm supposed to talk about that first. But anyway, that. Okay. The studies for comparison of error rate. Basically, what was suggested by the Brian Ripley is that you should just do using like actually running like full factorial experiments. Let's say you have three different models to compare. You actually run experimental design doing that and look at the test error. Okay. So it's an experiment and should be designed and analyzed as such. Okay. So here, this is from the study of comparison. I want to point to you this web page. Okay. It's from this book. Okay. This is an early textbook, 1996. Is more theoretical, but you do have like practical examples as well. Okay. It's like theoretical books such as like this ESL as well, but you do have some actual data and analysis in this game. It's about pattern recognition and neural networks, okay, by Brian Ripley. And here today we're going to talk about a data set. It's about some forensic classes. Okay. That, well, anyway, they have this information collected from traffic accident or something like that. Okay. Look at that. Or something else. Not just a traffic accident, I should say. Okay. They have all different kind of classes, and they try to analyze the contents of that, the neural contents of the classes. If you want to look at it, it's right here. I remember I purchased this book for $14. It's quite inexpensive. Okay? You may want to get one. It's up to you. Okay? Okay, so this was like I quoted from the Brian Ripley. It's experimental position, not just doing just for one spin. And comparison between classifiers will normally be more precise than assessments of true risk. So here, this is another view of assessing the goodness of models. If you have several models in view, you want to compare them and see which one is better. And you try to detect subtle differences in performance. Perhaps you need a larger data set. So this, you have small data sets, it's not easy to attain. Okay. Anyway, so here these are some ideas based on that. Let's just go through this quickly. It's measured by some kind of loss function. And what you have is you try to make inference about expected loss. Okay. So the test error based is expected error, like ERR. This is just expected loss anyway, by a certain loss function. Okay. Normally you see this square error of loss, right? Like in regression analysis. You sort of having a square error. L1 regression would be the absolute error. Okay. And for trend set, the estimated training error would be just error rate. We have basically the one that we obtain from confusion matrix, right? And that is denoted by this. And remember we mentioned about this. This is called apparent error rate, right? From training set. Apparent error rate usually is underestimate the actual error rate. Right? Remember we mentioned about that. And for the error rate for any feature vector, okay, if you have square loss function, basically it's decomposed into three parts. this irreducible error rate. This is subject to subject variation. So there's no way you can capture that. So irreducible error, and the square of bias of class variance. I guess we all familiar with this. Okay, and in sample error and optimism of training error. Remember we mentioned earlier, training error usually underestimate the actual error, right? So they come up with some kind of measurement about the optimism of the training error. Okay? So actually, it's basically this is remember this ERR is apparent error and expected error is so-called. We actually talk about this. This is called expected actual error rate, which is still not reflecting the real values. Okay? The optimism is defined as the actual in sample error and this estimated error rate. Okay? Hopefully, you want this to be 0, right? Okay. Actually, the slide says gradually bringing the model criteria. So you can actually just look at the final result. Okay. So optimism, so your in-sample error contains 2 parts. Okay. And second part, in certain condition, okay, for regression model with the inputs, basically, you can show that the second part, okay. Well, here the first part, this is what you have. This is one actually underestimate the true result, okay. And then here we have the covariance between the regression model with the inputs. Actually, this part is basically identical to this, okay. And actually, this is what some criteria is coming in here. Okay. So the Merrill CP is actually this sort of apparent error rate plus certain thing here. And this part, remember D is an input, right? Number of inputs. Okay. And of course, CP, Merrill CP again also penalize model complexity. Okay. If D become larger means more input variables, so you have more complex model, right? Okay. So you have this additional terms. Okay. Let's now look at what this notation stands for. This is what this is about. Okay. So all these model goodness criteria, they kind of follow very similar things, except that some of models stress more on model complexity, some penalize more on the error. Okay. And this is Akaike information criteria. Basically, the idea is that again, the second part, this is penalized model complexity. D is number of inputs again. Okay. And first part is the model information. Okay. This is -2 times expected log likelihood, meaning that how likely your model is. So that's model information. The second part is the model complexity. Okay. How complex the model is. With too many terms, then this archaic information become larger, and usually this is not what you want. Okay? So try to again balance on model goodness and complexity. Okay? I really want to go through this quickly, so then we go into that the one I talked about variable importance. Okay? Now here this is AIC under logistic regression. Okay, and Merrill CP is like very, in a sense, it's linked to the AIC very closely. So under logistic regression, basically, kind of just use AIC. They probably will just give you the same result. Use Merrill CP. And there are some models really hard to compare. For example, the nearest neighbor, right? We talk about nearest neighbor classification, right? Where you have to use, instead of say number of inputs, you have to use some kind of effective number of parameters. Okay. So again, still that if you link to that, still essentially the same model, well, the same criteria. Okay. If you have a too complex a model, then actually you try to penalize that more. That is an AIC. So if you have all this information combined, you can evaluate how good the model is. Okay. I try to just pass this. And Bayesian information criteria. This criteria penalize more on model complexity. Okay. So BIC tends to look for a simpler model rather than look at more like the model that give you like a better result. Okay. I want to talk about performance measure. Okay, on the second one. Okay. If you have insufficient data for 3 set split, what will you do? Remember we talked about this tenfold classification validation. Okay. So basically, choose cross validation using choosing the V fault. Okay. When V is n, basically you have just leave out one out cross validation, and basically this is more traditional ways of cross validating the result. Okay. That is in your trend set. Okay. In the trend set, of course, in this case, trend set is combined with validation set. Okay. So you use trend set not only for building up the model, you also use that to cross validate the result. Okay. And leave one out is that you're just taking all the observation except one to build up your model, okay, and use the one that is left out, the one observation left out to classify. Okay, of course that particular observation could be incorrectly classified, and from that information you can obtain say the misclassified errors. Okay. It's more time consuming doing this, okay? Because here that means you have to do n passes, right? Isn't it? Right? Every time you leave out one out and building model on the rest, and you validate this the left out sample, right? So you have to do n times. Okay? So more time consuming to do. Okay? And no uncertainty from cross-validated sample, and then so there's no way to measure the error. Right, this prediction error. And actually, among others, actually this will create some biases. Actually, in the literature, people suggesting about adjusting the bias that you use this leave one out jackknife. This is so-called jackknife method. Okay. And most overlaps among cross-validation sample. Okay. And result in larger variance but less bias. So actually, there's a trade-off. If V is too small, you have lower variance and sample size bias. And usual recommendation is using either 5 or 10. I think it's different also. They have different level of things. Okay. Brian Ripley suggests using 5. Okay. This Hasty et al. Suggests using 10. And in RPAR, the default is 10, so you can see what they suggested, right? 10 for cross validation, probably the one to go with. Okay. Bootstrap method is completely different than the cross validated result. In a package caret you can choose to do a cross validation. You can do repeated cross validation, tenfold. Repeated tenfold cross validation. You can also choose to use a bootstrap method. Okay? And bootstrap samples, the trained bootstrap sample as a training sample, and the original sample as a testing sample. Okay? So that is, you take a bootstrap sample from your data set, okay? And then you train your data set using the bootstrap sample. There's a potential problem with this is that a bootstrap error estimate may arise from overfitting, okay? And this probably because of overlapping observations. Right? In bootstrap sample is about sample with replacements, right? Okay. And then your bootstrap sample could overlap with training set, okay? And could overlap training set and test set. The same observation could be in your bootstrap sample and also in the test set. Bootstrap sample. Keep the IDs of this data observations in the bootstrap sample, okay, And when you try to evaluate the validated error, you just remove all the overlap observation and just fit the error on the rest. Okay? So here, this C minus I is a set of indices of bootstrap samples B that do not contain observation I. Okay? So that is, once an observation is used in the bootstrap sample, okay, you exclude that from the test sample, okay, when you try to evaluate that. Okay? I'm going to skip some of this for now, because I'll talk about variable importance. Okay. When you have two classes, and this is a way to find out variable importance without considering any model at all. Okay? And then this RC, okay, RC curve. Okay. And actually, you are looking for area under this RC, this curve. I think C always stands for curves. In our next slide, you will see that. Okay? And basically, we are looking for sensitivity and this specificity, okay, of these two cases. Actually, this is close related to hypothesis testing. Right? Sensitivity means true positive. Okay, and as type 1 error is false positive, right? Isn't it? Okay. And then the specificity is true negative, and type 2 error is false negative. So, okay, so we're looking at that. And true negative means power. Actually, that's power, right? Okay. So basically, if you have like two classes cases, okay, sensitivity is a conditional probability that, okay, if actual, say, subject is diseased, then you predict as disease. Okay. So that's successfully classified result. And we can apply this in our two classes classification. Okay. Because ideally, we want 100% sensitivity, which is usually very achieved, right? But at least we want this sensitivity to be as near 1 as possible. Okay. And basically, this is using in some community, they call this receiver operating characteristic curve, okay? So RC curve. Basically, it's used to assess the trade-off between sensitivity and specificity. Okay. The idea is to plot in sensitivity versus specificity. Okay. And we want that area under curve to be as near 1 as possible, and to indicate it's a good result. Okay. Now here, this is a figures I extract from Hursti et al. I should give a page number. I didn't give reference, but it's there. Okay, in that book. Okay. Basically, there are three models under comparison. One is tree model with this green line. Okay. Okay, and one is the GAM, which is generalized additive model. Okay. I guess that we're not going to cover at this moment. Okay. Some kind of model fitted. Okay. And now here, this is weighted tree. Okay. A weighted tree model, weighted against the priors and costs as well. Okay. So here, and the numbers in here basically give the area under the curve, where this curve is plotted by plotting sensitivity versus specificity. Okay, with a different. I guess originally each one is represent like different numbers of parameters. Okay. And overall speaking, in this case, look at that tree model. Well, this generalized additive model is the best. Well, I can see a reason why they advocate this. Okay, this is a model suggested by them, okay, by Hursti et al. and GAM is a standard edit package by this authors, okay, as generalized additive model. Okay. The idea is that, or the general editing model is that your response actually can be modeled by several chunks of function separately. That these several chunks of functions are edited to each other. Okay? So in a sense, they have something like this. Okay? They kind of model, for example, you could have some response. It's modeled as a f1 x. Here this is feature vector plus f2 x. Okay. This is only one possible way. I could have multiple of these models here. Okay. And the names say generalized edited because this is some more general. This is a general model than the usual model we see, and also the terms are edited. Okay. So here this is a function of feature vector, and here another function feature vector, and that's called general editing model. Of course, usually when they fit that, each one is approached by certain types of. So it's combinations of several functions there. That's GAM. Okay, that's called GAM. Of course, doesn't mean it's always good, right? It depends on type of data they fit. Okay. But here, anyway, here this is comparison. Okay. And the goodness of model is evaluated over several possible combinations of situations. And then here you plot this, and the area under the curve, basically just give you this the numbers you see here. Okay. So area under curve of this blue line, that's about 0.98. Okay. Out of total one, you have this square here. Okay. So it's just about 98% goodness. You plot sensitivity versus specificity. Okay. The other models just under comparison. That's this. Okay. And fortunately, R has many softwares implementing this, including this caret. We have this filter variable importance actually evaluating this. Okay, and this graph is for just one feature variable only. Okay? One variable at a time. So you can do this for so all the variables in the inputs. Okay. Here we're going to skip this for now. Okay, I guess we can go back to our class notes. I really want to go through this. Let's continue on this class note 10. Okay, last time I left out, and I modified a little bit today, but adding a little bit more at the end, so I didn't change much on the previous one. So maybe you want to reload this if you want. We talked about the first part about iris data fitting. And we talked about tennis data last time. Here, this is forensic glass data from that Brian Ripley's textbook, okay, in that website. Okay. There's pattern recognitions and neural network. Okay. I guess this is still true. I didn't see if they changed that. Let me see. Hope this is still the right one. Oh, it's ACUK PR, and this is right. Okay. Let's see. Yeah. Okay. So that's the right direction. That's the right directory to read this. Can you see from back row? Is it too small? It's okay, right? This is node 10.r. And forensic class data, you can read from this, and here just go through this step. This is I suggested doing that, but you don't have to do it this way. Okay? So I have this separate forensic class variable name. This is more descriptive name, but in the data set I still keep the abbreviated names of these variables. Okay? And forensic class type, okay, will be this. These are abbreviated names for that, and then here this is more descriptive name. So I kind of just put in like different folder, and then in the data set they explain that here these are the group identities of a tenfold subset. Okay. Well, here this is for illustration purpose. Suppose they have this 10 folds. Suppose various samples is already laid out. This is what you can do. Okay. So they already have that. Okay. So here we have this result. Let's say you save this into your R data. I probably already provided this somewhere in our data. Let's see. If not, I'm going to put it up. Okay. So you don't have to, well, anyway, you can go through that class note 10 to have this data set. I suppose I can put it here somewhere, okay, about this forensic class data. Okay. I provide a link to that. No, this is not that. So anyway, it's not there. But suppose you go through this, okay. You go through these steps, and then have this one, and then you save the data. This forensic class data set, and the more descriptive names of the variables. Okay, and then here this is the target variable, the more descriptive labels of the classes for the target variable. And now here this will be the group ID for this tenfold validation. Okay. Suppose you store that in this class data. You can later on just attach that or load it. You can do attach if you want. One way of doing that. And the quick way to do it is using the loading the data. Okay? So let me show you this. So actually here currently I have this 8 objects in my working space. Okay? And quick way to load the data. Suppose you already create this data, and next time you go into R, you already have this. You use a load workspace. Okay? This is a quick way to load that. Okay? And of course, then you have to search over that. Currently, I have that in the data, so I have this forensic class data. So you open that, okay? And you can see now it's part of your data set. Okay? So you have forensic class, the tenfolds, and class types, and renames. Okay? So assuming that every step is okay, consider now. Let's say we already have a data set. Okay? Let's run a couple of this. At least we get some descriptive result about this. So here we require our lattice plot, and here this is the part we need. Okay? Here this is the trellis display of the data. Okay, according to here. We have all total of 9 descriptive feature variables here. Okay. They are all. I think these are all the names for the ingredients, right? Isn't it? I'm really bad at the chemistry, so I don't remember all of them. I know some of them, but not all of them. Okay. And this we know. This is iron, right? Barium and sodium. Okay. Still, I remember some of them. But well, this is not descriptive enough. Then of course, then you can always do that. Okay. Remember, in here I have this forensic class names already assigned, so maybe this is a way that we can have it. Okay. Let me just show you that. Okay. These are the variable names for that. So I store data in this way. It's very convenient, so I can update, my graphics and make it more informative. Okay. except for the last variable, which is our target variables, of course. So here, these are the variable names. Okay, more discrete names of this metal here. So let's just do this. Okay, so revise our graphics here. BW is our box whisker graphics, and revise the dimension name, and you can replot it. Okay, now assuming that I rotate the, see, look at that originally. See, they all come together. Especially now, you try to make this more readable. You can do rotation here. So basically, I just rotate the x-axis label 30 degrees, so make it more readable. And by default, variables goes this way: 1, 2, 3, 4, 5, 6, 7, 8, 9. This is like, this is reasonable because that's a coordinate system. If you want to use it as a table system, you can use as table equal to. Okay, so basically, what is that? So you update, just update this box and whisker plot. Okay, so we have this result. So maybe 30 degrees is not good enough. So we want to rotate more anyway. Okay. So anyway, we have more discrete names for that. Okay. Oh, okay. So we have of this iron, among others. There's another one. This is not really of this any iron, but it's reflexive. It's a reflexive index. Yeah. So here, more discrete result of this plot. And here, this is yet more informative plot. Okay. Originally, I arranged the variables in this way, right? Okay. Row-wise, from left to right, from bottom to top. Okay. If you use as table equal to is from left to right, from top to bottom. Okay. So that's either way we want to arrange this in this way. And actually, I start with this as table equal to. Okay. It's done by that. Okay. So let's look at a more informative plot. We try to have box whisker plot, okay, of all these variables, and we make that graph type more descriptive rather than this. How to understand what these are, okay. And then I do have this. F graph types actually give more descriptive names for the different classes, right? We actually can see that there. Okay. Abbreviation, but here these are more descriptive names for each variable. So you can make it more descriptive by running this. Just run this anyway. So it's going to be the result like this. So maybe 30 degrees is not enough. So increase this. Make this a full page tape graphic. So here, this is comparison of that. Well, at least we can see the variant here, right? It's like, well, this one stands out, right? Isn't it? Okay. So this variable is a good indicative of, like, or at least separate the vehicle head length from the rest, right? So forensic graphs, not just for traffic, the result from traffic accident, but for all kinds of glasses, pieces of glasses, they try to see where it comes from and what kind of material, what kind of measurement, like reflexive index we have. Okay, here just revise that how it's not. Okay. It's not informative, so here we have this result, and then here make a change again. Because all these are too large, it's just come together, so you can change the size. Okay. You can change the size of the fonts here by doing that. Okay. So hopefully this will make more sense. Okay. And one of this here, I use this scale at y-axis free, because the reason is that the scales of these variables are all different, so that's why I use that. Okay. Use a free format. Otherwise it will use like identical scale, which is it's going to ruin this class. Okay. Some of this will not be. You won't be able to see the difference. So among these graphs, this class. Which variables other than variant you think probably more useful in the classification. Probably not silicon, right? It's hard to tell for that, okay? Distribution is almost like the same. Probably some of this, so all combination, probably combination of these different things we can actually make sense of the data set. And there are 1, 2, 3, 4, 5, 6, 7 class, 6 classes of interest, right? Not just 2. Now let's look at for this forensic data again. Let's look at our tree model. Here we're talking about running the tree. And here is a control parameter. Here this is complexity parameter. Okay. The number we set here means that this is much of the improvement you would expect. Okay. To go down to the tree. If the complexity parameter doesn't improve by this much, okay, it will not further grow the trees. Anyway, so that's the idea of that alpha. Anyway, let's look at the plot. Okay. So let's plot this data, this tree model, and see what we have. Really hard to tell, right? They all mess up. So many things are printed out there. So maybe we want to use a different font size or like this. And then here, this is a command that allows you to look at a particular path. Okay. So here you do path.alpha and left click on graph to identify nodes for paths. For example, okay. Let me type this. When you do this, let's say, suppose I'm interested in knowing this, okay. This node. Okay. So you left click, okay, on that, and we're also trying to understand this node. Okay. Hopefully this is good. Okay. Left click on that, and then you right click on start. So actually we are selecting this node and this node. So basically the first node we selected the node 15, and about this. So here this is criteria go down to this, right? Okay. And this probably is not helpful because we want to know where to cut the tree, right? Okay. And here these are the CP value, complexity parameter value that we have. Here you're talking about number of splits among different models, okay, and relative error and cross relative error. And still this is hard to see, to perceive, and we use a graphic to plot the CP value, this complexity parameter, and use one standard error rule. Yeah, this is CP plot. We don't use the model. This is wrong place. Ignore that. Anyway. Okay. So here, this is the size of tree. On the top, this is 1 node, 3 nodes, 4 nodes, 5 nodes, and so on. Right? And on the bottom would be the complexity parameter. And vertical axis would be the cross validation relative error. Because we expect the error as small as possible, but at the same time we also do not want a too complicated model, right? Okay, and this slide basically talking about one standard error. So remember, idea is try to find a tree model that just go below one standard error, and at the same time the number of nodes is minimized, right? Okay. Definitely this is not the one we want, right? Isn't it? Because again, here is part, or this is already up above the standard error. This one is hard to tell. Probably you still have a chance to go about one standard error for that. Okay. So anyway, something in between. Here the result is 0.041, and what's the scale of this? This is not equal scale. This is again the log scale, I think. Here this is 0.12 and 0.068, 0.041. I think they are equidistant in the log scales, but here it's hard to tell. So maybe this is the one to go with around this area, so that's about 0.01. Very hard to tell from this graphic. Now you have to look at this at the 0. Where is 0.01? So here we have this one CP of this at the number of split, okay, 5. We have this CP of 0.03, and the arrow close value is arrow would be about 0.57. I think that's around this one, okay. So we try to choose the one that is closest. That is closest. This one probably 0.01. So let's say you want to cut at 0.01. Let's try this out, okay. So this is about like 8 to 9 nodes of the trees, okay? About 8 nodes or 9 nodes, okay? So let's try to say we want to cut this tree, and we want to cut the CP equals 0.01. The command to prune the tree is this, PRUNE, okay? Of the tree model with just growth, and with a CP cut at 0.01 with complexity parameter of 0.01. And we store the result in M2. Here, this is our new tree. This is the prune tree. This is already okay, downside. Okay. So we have this result, and then you can plot this tree again. Let's just run both commands and see prune trees now. Still some hard to tell, right? Let's increase the size a little bit, you can see better. Okay. Why we need some kind of render, other types of render instead of, remember there's way to have different views of this tree. Instead of default, you can have this, the branches going this way, right? You can say branch equal, what was that? Branch equals 0, for example. Have a better view of this graph. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. There are total 9 nodes left in this tree model. So here, this is the result. We kind of downsize the result, and then you can print the summary of this result, okay, of this tree. So we have CP at this 0.01. We have this number 3, 8, so it means 9 nodes. Let's go with that. Okay. Now, if you like to render this in different view, use this party kit. Remember I mentioned about that. Okay. Assuming that you already have this installed, okay. Well, you need to install this package, of course. So let me say require this party kit and then plot the result. Okay. Oh, I like this better, okay. Except that there are too much information given there. I think there's a way to change the size of this font, so make it easier to read. Okay. It's really hard to read, even this, right? You can change the font size of making this. Okay, actually, these are bar plots. Okay. So bar plots are different classes. Okay. And there are 6 classes. I don't know if we can have. I know there's a way to change the size of that, but I didn't get into the detail of that. So we can change the size and look at it. Well, of course, here we have just way too many. We have too many classes. Of course, if you train the tree even more. Okay. Let's just look at 0.1 for the time to see what we got. How about that? Right? Let's try to find a simpler model. How about 0.5? 0.05. And then let me change that to M3. So we have M3 now, and see we have better result. Are we better off now? There's no. So give you a better views about these are the bar plots, right? Of the 6 classes. Of course, still hard to tell. You have to go back on the different classes, the name of different classes. And basically for this node, okay, this node, the winner is this class, right? Number 5, right? So you can see that. Okay? You can see this result. And classify according to this variable 1, 2, 3, 4, 5 variables. 4 variables, right? AL again used here to split. You can see that. Here we have AL split there. Okay. So in this case, on variable, only 4 variables. Okay. Attached. Did I say the case study due on Thursday? I don't have time to continue this today, but actually there's a class note, okay, related to that is node 14 and then node 14.r. Okay. Here I talk about variable importance. Suppose this, I think I didn't do reorganization of this one, so this is like supposed to be the later class note, so bring this up first. Okay. This is about variable importance measures, okay, major importance of variable in regression and classification. Basically model-based approach or filter approach. Okay, the one that you can use a Harvard filter approach unless you do some specific model like tree model, like logistic regression. Okay, they have some model-specific method. Okay. Filter approach is like each predictor variable is very individual for each importance, and actually the measurement used to evaluate the importance is this ROC. What is that? The area under ROC curve. Okay. It's done by that. The advantage of model-based measures, of course, is closely tied to the model performances. Okay. This is model-specific. Okay. Variable importance. Okay. And can incorporate the predictor's covariance structure into the calculation of measures. Okay. And let me just go through this. I talk about this variable importance in measures in caret. So for most classification model, each variable has a separate variable importance for each class except for classification trees. Okay. At the moment, we didn't talk about back trees and boosted trees yet. Okay. So some of this we have to skip. Okay. All measures are scaled to have a maximum value of 100 by default. So basically, this is variable importance. Okay. And available model-based measures include only this. Okay. They probably keep adding things like this is for this model FDA. This is flexible discriminant analysis. So including our tree model, random forest. Okay. And this is generalized boosting map models and classification backend linear model. These are model-specific variable importance. Okay. Currently, is probably want to run the second approach using filter-based measures. Using filter, the command to use is filter variable importance, okay? and with this argument. Okay. So basically, filter variable importance is actually very this. For 2 classes case, for each predictor, a series of cutoffs is applied to predictor data, and use the ROC curve. For multi-classes, you do a pairwise classes. And look at the maximum, okay, ROC. Okay. And that's called variable importance. And actually, of course, we care more about how we actually do this in R. Let me refer you to node 14.r. I don't think I can go through that today. It's right in here. Okay, explain a little bit here. Again, this is from forensic glass data. Okay, this is filter-based variable importance, not depending on any kinds of model that we mentioned. So this is actually is run under ROC. Okay. Okay. So anyway, I did this for you for now. So you're okay to turn in case study? Is it? When did I say the case study due? Huh? Not Thursday, or is it Thursday or the coming Thursday? Right? So if you really want to incorporate variable importance, use this one, filter variable importance. Okay? You can do it without knowing the detail how they come up with this, but it's using ROC curve. Okay. The command to use is this one, filter variable importance. Okay. Now here this is data frame of your feature vectors, and here this is target variables. So basically, in our case, German credit data, this is kind of good debt credits, right? And here, this is the remaining columns. So actually, it should be very similar. You should be able to get filter variable importance by doing that. Anyway, I have to stop now, and then you can, for the one that we use for adult data set, how you plot the result, right? Remember we have examples like this. Except that in the adult data set, I didn't use filter variable importance. So just take this for example, okay? So do you feel comfortable with the case study? Which is
Do I have to use the importance?
no, you don't have to. I just say in case you want to use if you're using variable importance here, it's a filter variable importance. Okay? I guess I have to say this. You are not responsible for doing this. Here, this try to help you on understanding things also about this variable importance. Okay?